do my 0 to 10 for r dr, and then times my pi over 6 to pi over 3 for theta d theta. 1/2 r squared, so there's where the 50 came from. Or at least I remember you saying a 50 in your answer. So yeah, 50 will contribute to the answer. And then this becomes 1/2 theta squared. So 1/2 upper limit squared, it's going to give me that, minus 1/2 lower limit squared would give me this. So be careful with your pi fractions. That's actually pi squared over 18.
So
Pi squared over 18 minus pi squared over 72. Let's see. 18, does it go into 72? Well, 9 times 8, so 18 times 4.
If you
Right.
multiply the 50 through,
Oh.
you get
Easier to
25 pi squared over 9 minus 25 pi squared over 36. And if you multiply both of those by 4 over 4, then
So you get an easier common denominator in that case. Okay. Well, I already figured out, since that's 18 times 4, that'll become 4, that'll become 72. So 3 pi squared over 72 times 50, and then you can cancel. Really, with 2, you can only cancel with 2's, right?
mm-hmm.
But then, hey, look, 3 over 36, hey, loving that. So finally, what's left after all this hodgepodge? 25 pi squared over 12. Is that what you got?
not exactly, but mine.
25. Cancel the 2's, 25 and 36. Cancel the 3's, 1 and 12. So you're left with the 25 pi squared over. That should be the answer,
Yeah.
I think.
Yeah.
So I'm a little bit nervous about some of the supplemental problems that I've assigned because, again, they're based on having the Calc3 experience from the beginning with me. Let me pull that document up real quick. The polar supplemental problems. I mean, a handful of them give you the graph of the region and, you know, kind of make it straightforward as to what your double integral is supposed to transform to. Like, you know, sometimes they mention a circular region, you're integrating R, your integration region R here is the upper half of a circular radius 3 centered at the origin. So that kind of lends itself to polar. But notice you don't have the x squared plus y squared love there, so you got to fall back on x equals r cosine theta, y equals r sine theta, and do the brute force method of converting it into polar, okay? But you'll still get an extra r. Same thing with this one. No polar love in that integrand, you got to fall back on the raw method. X equals r cosine, y equals r sine. But your underlying region is the first quadrant region enclosed by this circle, the line y equals x, and the line x equals 0. Do you see what that looks like? Circle of radius 5, y equals x equals 0 in the first quadrant. What would your r limits be? 0 to 5, because that represents the radius of the circle. Now, what's special about the line y equals x and x equals 0 in the first quadrant? How's that going to help you get your theta?
It's going to be between 45 degrees and 90 degrees.
Yeah, because x equals 0 is this, y equals x is this. You're spanning into the circle of radius 5, so theta should go from pi over 4 to pi over 2. It's okay to think in degrees, just make sure you're right in radian. You had a question?
I got pi over 2. I mean, if you want to check my
Pi over 2 for your answer to the last one?
Yeah.
You should have a squared pi.
Well, I got
Because you integrate theta as 1/2 theta squared. And so if you plug pi over 6 in for that, that should be pi squared over 36.
pi squared over 36.
And then that should be pi squared over 9.
Pi squared over 9.
So,
I know what I did. Yeah. Okay.
Okay. All right.
Sorry. That's the
The one that kind of brought me,
So
I guess, to the concerning point is one like number 9. These are all set up as volume problems using polar coordinates, and that one might be kind of tricky because you may have not, or even maybe number 6, okay? A lot of these don't have pictures, and I've already had to, I guess, tell you that I'll need to probably give you some pictures to incorporate with some of these images. Number 6, you're asked to use polar coordinates to find the volume of the given solid. The solid described in number 6, again, pay very careful attention to the prepositions in the sentence, okay? You know, locatives like below, beneath, above, you know, between. That kind of gives you an idea of how to visualize some of these things in space. So it says, the region you're looking to find the volume of is lying below the paraboloid. So whatever a paraboloid looks like, I'm underneath it, is where the solid is. And above the XY plane. So another preposition that's important, above the XY plane. The XY plane is the base of this solid. The solid material is from there up to the paraboloid because you're lying below the paraboloid and above the XY plane. There's where your stuff is, okay? Could you turn that function, I mean, that's going to be what you're having to integrate, since that function defines the top of the shape. You'd integrate this, but can you see what the underlying region would be where that paraboloid hits the XY plane? How do you take a surface and determine what it looks like when it hits the XY plane? Make z equal 0. You're essentially wanting to do the XY trace of the surface. So if I set z equal to 0, look at the equation that you get.
Y squared equals 4.
Yeah, you get 5x squared plus 5y squared when you bring those over. Factor out the 5, divide it across. It whittles down to x squared plus y squared equals 4. Circle of radius 2. So if you're looking to find the entire volume between the xy plane up to this paraboloid, no first octant isolation is mentioned here. You'd want to integrate that, convert it to polar. So notice factoring out the 5 might help there, because when that negative 5 is factored out, x squared plus y squared, that converts pretty easily. What would your polar limits be based on the underlying region?
0 to 2 pi.
0 to 2 pi for theta, and it was, the underlying region was a circle of radius 2, so 0 to 2 for r. Well, so if you're going all the way around, not saying first octant, anything mentioning first octant pretty much is going to guarantee 0 to pi over 2 for theta. But your r would still go from 0 to 2 based on the circle being radius 2. Probably one of the hardest ones here is number 9. Yeah.
I'm just wondering, earlier we had said that it was a restriction of 0 to 2 because of the 0 to 2 in the answer, but it didn't say that there, so.
I know. See,
Or
that's
the
the
question,
thing.
I meant, the 0
This
to 2
one-
question.
The way these are set up is you don't have to graph the solids or graph the surfaces, but you got to be able to discern using these prepositions what's the top thing that I'm integrating.
Yeah.
If it's lying below this paraboloid, that's what I need to integrate, because you always do the double integral of what's on the top of the
I
solid.
guess what I'm asking is that it doesn't say
And
that it's
then-
just in the first octant or anything like that,
No.
in the first quadrant of the XY plane, so it wouldn't be the entire
So yeah, you didn't
plane,
you
it
missed
would
that
be the
discussion.
positive and negative?
Yeah, we did that a
Oh,
second
I'm
ago.
sorry.
We talked about 0 to 2 pi for theta and 0 to 2 for r. So yeah,
Well, the
if
0
there's
the
no
0 to 2
the only
part
mentioning of the
was-
first octant is going to almost always guarantee 0 to pi over 2 for theta. That's usually the only reason the first octant may
Yeah, I
have been
got that. I
mentioned.
was just wondering about the 0 to 2 for x, because I'm sorry if I'm taking this off track.
No, are you talking about
It
number
was
6?
earlier when we said that it was, so we only
Matthew,
have
are you talking about this one?
yes, sir.
Oh, okay, I was just making sure. I didn't know if you were on this okay,
Yes,
so
so
0 to 2
you were
for
saying
r.
that the right, only the right half of the circle in this would be our area that we would find the volume for of that underlying paraboloid.
For that previous problem.
Yes, but for this one, it doesn't say that it's
No.
only 0 to 2, so why would we go
No,
negative 2 to 2?
What you have to do is you have to set z equal to 0.
Okay,
This surface, opens downward and it hits the XY plane.
Okay.
Where it hits the XY plane is where you get your underlying region from. So if you set z to 0 in that equation, and notice you can, is it 20? My bad, not 25. And factor your negative 5 out. And then instead of solving this for x or solving it for y, start thinking of x squared plus y squared as your quantity you want to solve for, because that leads to circular regions most often. So if I bring this over, and then divide both sides by 5, that lets me know when this surface hits z equals 0 at the xy plane, the underlying region is a full circle of radius 2. And is this surface above the inside of this circle, or is it above the outside of this circle?
so,
In other words, there's my underlying region. Is the paraboloid above this, or is the paraboloid above this?
the inside.
Well, yeah, it's above the inner. Why?
Because
That's where it's
above
defined.
parabol.
So where it's defined, it's essentially kind of the domain of the double integral. I mean, if you start, with the z-intercept, if you let x and y go to 0, it goes to the z value 20. So here's x, y equals 0, it's way up here at z equals 20. It opens down on the z-axis, and that's where it intersects the
So I
xy
guess
plane.
so we extend radially outward as we were speaking about before whenever we solve this. Okay, I got it.
Okay.
Cool.
And anytime you're doing a volume problem, volume in xy coordinates or in r theta coordinates is always the double integral of what's on the top. The region we're looking at is below this parabola, so therefore, because that's a underneath kind of preposition, that's what's on the top of the solid. So I need to do the double integral of this over that domain, circle of radius 2. Doesn't say first octant, so it's all the way around. So you'd use 0 to 2 for r and 0 to 2 pi for theta. Okay? But let me give you a hint on this one right here, number 9, because that's going to have a tricky visualization with it. Okay. Who do you think so? So, again, same preface of instructions. Find the volume of the solid described in the region, described in the sentence. The region we're trying to find the volume here lies above the cone. So the cone's equation is given, and it's also named as a cone. Can you see that in 3 space? Here's the xy plane. There's the origin in the palm of my hand. The cone opens up with its apex there at the origin, well, I guess it'd be an inverted cone from the way we're looking at it. It opens up like this. Okay.
45-degree angle.
Yeah, 45-degree angle in all directions. That's a beautiful thing to remember, especially when we get to spherical coordinates. Yes, know that. So yeah, that's a cone opening up from the xy plane. Makes it 45 degrees off the z-axis is noteworthy, I guess, at some point. But like this. So the region lies above this cone, above the cone. So here's the cone up above it. There's where our region lies. But at the same time, it lies below a sphere of radius 2. Can you see what that region looks like? The cone's below. It's lying, well, the cone's, it's above the cone. It's below the sphere. So can you get a mental image of that shape?
So you're trying to find the inside of the ice cream cone?
Yeah, the inside of the ice cream cone, the cone shape itself, and the little bitty muffin top on the top that, it kind of looks like a little yarmulke, I guess. The little cap of the sphere that you're cutting off. Okay? So it looks something roughly like this. If you look at it as a cross section, here's the xy plane, and I'll go ahead and draw a little dotted z-axis right here, going upward. And go ahead and remember what Nicholas just said. That cone equation is always going to give you a 45-degree angle off the z-axis in all directions. So as the cone opens up from the xy plane, I don't need that in this particular problem necessarily, but at some point when we do 3D versions of polar coordinates next week, it'll be noteworthy to know that there's a 45-degree angle there off the z-axis. But here it's just, the cone opens up, a sphere of radius 2, and how do I know that's a radius of 2?
Square root 4.
R squared 4. Okay, so sphere of radius 2 would kind of meet the cone looking something like this, roughly. Okay, my graphs are getting kind of sloppy tonight. But that's the kind of like a cross-section, a lateral view of what our 3D solid looks like. So if I tilted this a little bit, you kind of see it look like an ice cream cone. You'd have the cone pitched up like this, the spherical cap on the top, but then you see some subtle, I guess, circular curvature right there where the cone hits the sphere. So yeah, you're finding the volume of an ice cream cone, essentially. So now this is a little bit different because all the other volumes we were describing go from what's lying on the top all the way down to the xy plane. In this case, the volume has the sphere being on the top, but you're not going all the way down to the xy plane for the solid that you're making. Your sphere's on the top, but the cone's on the volume, on the bottom. How would you set that up as a triple integral or a double integral?
It's going to be r squared r dr d theta between 0 and 2 of r and pi over...
Not quite 0 to 2 for r. First things first, let's double check what the integrand is going to need to be. Do you recall, and hopefully you do, in Calculus 2, the first kind of areas you were calculating were from the graph of a function all the way to the x-axis from a to b, So this turned into the integral from a to b of f of x to dx. Later on, you wanted to isolate the area between two functions. On the integral from a to b, what did this change your integrand to? You did an integral from a to b, but what was your integrand?
f of x minus g of x.
F minus g, the top of the region minus the bottom of the region, to isolate that area between the two curves. Okay? This is kind of analogous to that. The equation of the sphere on the top, can you get a good marker? It comes from x squared plus y squared plus z squared equals 4. I'll need to solve that for z.
You need to take out everything.
So what would the sphere's equation become if I converted just the sphere's equation to polar?
Square root 4 minus r squared.
Z equals the square root of 4 minus r squared, because you keep that x squared plus y squared quantity collected together. So the sphere becomes this. I'm not using the integral yet, so no extra r needed until we start talking about the actual construct of the integral. Now the equation of the cone on the bottom. The equation of the cone, I've hidden it. There it is. Ta-da! I mean, and you could take this also. You could replace x squared plus y squared here with r squared, and then solve it for z. Subtract the r squared from 4, take the square root, the positive square root, because you're on the top half of the sphere, where z is positive. What would this equation be if you converted it to polar? Z equals r. Yeah. That's pretty kind of awesome. Kind of pretty awesome. Yeah, pretty kind of awesome. Yeah. Either way you want to say it. So, if you think about the whole f minus g analogy from Calculus 2, to isolate the volume between the cone and the sphere, the role of the top function, the f, that you're subtracting the g from, would be the sphere. So this should become, and let me jot down what I got. There's the polar equation of the sphere. Here's the polar equation of the cone. So I need the double integral. And you've given us some of the limits, I think, Nicholas, but I'll double check it here in a second. So top minus bottom would be the sphere's equation, since it's on the top, minus the cone's equation, since it's on the bottom. And then, since we are committing to a polar conversion, there's the extra r that I need, dr d theta. Now we just need to figure out those limits. That I'm going to leave to you, because I don't want to completely set up the homework problem for you. But here's the thing. Nicholas, I think you mentioned 0 to 2 for r. The problem with 0 to 2 for r is if the sphere comes all the way down to the xy plane, the sphere's intercept would be a radius of r. But the trick you've got to figure out is I'm not going all the way out to where the sphere hits the xy plane. I'm stopping right there where the cone intersects the sphere. You actually have to project this downward to find out what circle that would be for the underlying region of the ice cream cone.
That'd be 4 cosine 45.
No. Not 4 cosine 45.
Radius.
Radius isn't 4.
Yeah,
Radius is 1.
Yeah, but you're looking to project this distance down to the xy plane, but that distance isn't 4.
Okay, I'm still thinking diagonal,
Yeah.
not radius.
But yeah, that's a darn good hint. Because knowing that 45-degree angle actually, I guess, does come in handy in this case, if you know that makes a 45-degree pitch. Because the radius of the sphere is what that represents right there. It's part of the cone, but going from here to the outer edge of the sphere, that has to guarantee to be a full radius of 2. So if I want to project that side of the cone straight down to the xy plane, well, what would that guarantee that radius of the underlying circle to be?
This is just cosine
2
2.
cosine 45.
It's 2 cosine 45 degrees, better known as root 2. Yeah, so this distance is square root of 2, that distance is square root of 2, because notice you can do the Pythagorean theorem on them. 2 and 2 equals 4, and that's the square of the radius. So yeah, practically done it for you. All right, let me see. What about number 10? Let me see if number 10 works similar to number 9, because you've got something on the top and something on the bottom. The solid doesn't go all the way down to the xy plane. let me give you about 4 minutes. See if you can browse through this one. And again, pay very, well, I guess the only preposition here is, well, there isn't really a preposition, I guess. But can you tell which of those paraboloids would be on the bottom and which one would be on the top? I'll at least let you start with that advantage. Z equals 5x squared plus 5y squared is the bottom, because this is a paraboloid vertex at the origin opening upward. Okay? This one, 14 minus, bless you, x squared plus y squared. And again, maybe factor the 2 out there. That's a paraboloid that starts at z equals 14 and opens downward. So you've got one that opens up, and then up above it, another one opens down. So they have to have a point of intersection, or a region of intersection. So see if you can figure that out and set it up as a double integral in polar. Shall I play the Jeopardy game? I've got it on my phone. Oh, hey, look, I just noticed the asterisk in number 8. For volume between two surfaces, use the double integral analog of area between two curves with integral of f minus g. Okay. So converting the paraboloids equations, you need to do that eventually. If you convert this one into polar, it becomes z equals what?
5r squared.
5r squared. Because you can factor the 5 out, and boom, there's your x squared plus y squared. What about this one?
14 plus 2r squared?
14 minus 2r squared.
Minus, I had minus, I changed it.
Because you can factor minus 2 out of both of those, and notice it would change that to a plus right here. And then factor the 2 out as well. Okay, so your integrand, when you set up this, since this one's on the top and this one's on the bottom, it should be the double integral of this one minus this one. I guess I don't really have to have it. And then we're committing to polar, so that means I need the extra r And then d r d theta is the usual integration order. And no one's mentioned that yet, but it may be too soon for you to have asked, to have been prompted for that question. Almost every polar integral I've ever done, I've just committed a d r d theta order unless I factor it. I mean, but
I just need to commit to mine.
it's just whichever is convenient.
I was a lot more nervous before I started this problem than I am now looking at, you know.
So did everybody set that up right?
So,
Now, what's your R limits? The trickiest thing is the R limits of integration.
0 square root of 2.
0 to square root of 2. And the reason why is because you need to come up with the curve of intersection where this paraboloid hits this one, okay? So let me talk aloud. I've actually got these things graphed on the software package over here. But currently, and I don't think you've seen me graph using polar coordinates before, but this software package does let you graph using, does let you graph using the polar r and the polar theta. So instead of using x squared plus y squared, I just replace that with r squared, and it recognizes it. So there's one parabola that opens up from the origin upward. The one that's opening upward is the z equals 5r squared up there. The one that's opening downward is from the z-intercept 14, and unfortunately this isn't, this is opaque, you can't see through it. The z-intercept's at 14, it opens down, and it does intersect this other parabola at some point. So if you notice over here, we can change the values of r that are used. If I change r from 0 to 1, it'll actually slice up the surface. But then notice that's not the full thing. We want the complete enclosure by the bottom paraboloid opening upward and then capping off where the top paraboloid opens down. So if we could figure out that r value where they meet, then we're golden. So what you had to have done is just to set the two equations equal to each other at some point. Set the paraboloid on the top, which is 14 minus 2r squared, set it equal to the paraboloid opening up from the bottom, 5r squared, and then solve this for r, because that will kind of project it down to the xy plane to let you know what the underlying shadow circle is, representing the r and the theta domain. So if I solve this for r, add that 2r squared to both sides, divide both sides by 7, and just assume a positive square root for convenience. Don't have to worry about the negative values of r. R would equal the square root of 2. So the square root of 2 is about how much? 1.41-ish. Would somebody crunch that out for me real quick?
1.4142.
1.4124. So let me change my r to 1.41241-ish, something like that.
1.414.
Okay.
1.414.
Oh.
2. 1.3.
Or 2.
Like that.
Yep.
Actually,
About.
1.4.
And there you go. That seals the gap. At exactly an r value of square root of 2, and that's our rough approximation of it, you're guaranteed to have a flush fit with that upward opening paraboloid and that downward opening paraboloid to isolate the solid you want. So the solid we're looking for is all the mess on the inside of that.
Anytime that we want to find intersection, we just set the two equations equal to each other.
Mhm.
Okay.
And see what you're actually doing, see the polar domain is still down here. So when you're turning that into a polar domain, this intersection right here is kind of being projected down to the xy plane, kind of like a
No one's actually
shadow.
really blatantly told me that until right now.
What's that?
That if you want to find the intersection
Of two surfaces?
two surfaces or anything,
Yeah.
you just set the equations equal to
Just
each
set,
other.
if they're both solved for z equals blah and z equals blah, eliminate the z by setting the blahs equal to each other, and then
Okay.
and you'll get a two-dimensional curve that represents where they intersect. So up here in space, this is that circle of radius root 2, but we project it down to the xy plane, so it represents the, I keep calling it the shadow of the solid. I mean, if there was a light source up here, you kind of see one that's off skew over there, but if there was a light source, due north in the z-axis shining down on this, the shadow that would project down to the xy plane represents the underlying region that we use for our integration region. It will project down to that circle of radius root 2, so you have 0 to root 2 for your r. Nothing mentioned about first octant, so that means you're wanting the full volume all the way around. And now if you wanted to, I mean, you can, in some cases, use symmetry to your advantage. If you had a solid picture like this, you could say, well, if I did 0 to pi over 2, I could just multiply my answer by 4. But as long as one of your limits is 0, that's usually pretty easy to begin with, so you might as well just go all the way 0 to 2 pi and get the full thing, okay? So that's the solid you're looking for in that problem number 10. The tricky part is knowing that this curve of intersection is what determines your domain in that double integral.
Now, what do we use as our limit for pi?
For theta?
For theta, yeah. Pi.
Theta. So when this projects down, let's see if I can do it here. That's pretty close. So we've now kind of projected this down to the xy plane. I know you can sort of see the relief there and the shape of the parabola, but imagine this is now projected down as a flat circle to the xy plane. There's the positive x-axis. Sorry, it's a little askew. There's the positive y-axis. And since the problem doesn't mention anything about first octant, we're not just doing that part. We're doing all the way around. So your theta limits would be from 0 to 2 pi. Mhm.
Excellent.
0 to root 2 for r in any direction, that represents a projected circle of radius root 2. So 0 to root 2 in any direction, 0 to 2 pi for theta. Okay. Any questions? If I remember correctly, I screwed one of these problems up. Because, well, you've already seen me make mistakes. Because I recall this from last fall semester. I think I screwed up the one with the cone and the sphere. I think I screwed up number
9.
9. I think the integration is supposed to have sphere on top minus cone on the bottom. And we set up the integral here a second ago. It was this one right here, number 9. Yeah, the double integral turned out to be this. I think I reversed that. And I actually went for the region that has the cone on the top and the sphere on the bottom, which actually is sort of a different region.
I didn't like that answer.
I mean, you can do that, but you're limited by the radius of the sphere. So I think I've screwed the answer to number 9 up. So when you check your answer to number 9, it may be number 9. I think it's one of those, but I can't remember exactly which one it is I screwed up. I had to go back to my last fall D2L page and see which one I had to edit.
Yeah, that'll be like weird in a way.
Yeah, it would be, if you want the one that has the sphere on the bottom and the cone on the top, it would be like this all the way around. It'd be like
An hourglass.
well, but this is a void in the center. The only solid part's right here. So it'd be like a napkin ring, maybe?
Yeah.
It's the only practical use I can come up with that shape. I mean, there's probably some kind of, cone fit here, sphere fit there, maybe there's some kind of bearing, I don't know.
Yeah.
But yeah, that's not the region I want you to find the volume of. I want it inside above the cone and below the sphere, so it actually looks like a proper ice cream cone. Yeah. But we partially set that one up, so that one's almost like, 90% done for you. Except for the whole calculus part. All right? So this ends test 3's material. So in case you missed the announcement earlier, I pulled out a copy of the little calendar that I gave you a couple of weeks ago, and I decided, I'll get that back out, where did I put it?
I've never found it on Sunday.
It's here somewhere. Oh, here it is, here. So all I'm doing is basically interchanging what we would have done next Tuesday night on polar integrals. I've moved that here to tonight, the 9th. And I'm taking what we would have done tonight on triple integrals, and that's going to begin test 4's material next Tuesday night. So we're not behind. We're still going to be able to get covered all the stuff that I want us to get covered. So, but since this stops test 3 stuff, I want you to have the weekend to kind of get the homework absorbed, to get everything hashed out, and get your, if you have any questions, come back next Tuesday and ask me some questions on the test 3 material, and then I'll start putting the test 3. I mean, I can put it in there from Monday to Saturday next week. Anybody wants to try it on Monday, you're pretty solid, bulletproof, want to take it early, and leave it there through Saturday whenever you want to take it. Pardon?
I have other things to do.
I imagine you do, Mr. 26 hours.